Hey everyone, and welcome. Today we're going to pull back the curtain on machine learning. Now, I know it sounds super technical, maybe even a little intimidating, but really, at its heart, it's just about teaching a computer how to learn a new skill, just like you would teach a person. So let's just dive right in. I mean, seriously, think about it for a second. Your inbox right now is probably stopping dozens of junk emails from ever reaching you. How? It's not magic. It's a machine that has learned what spam looks like. It's learned to spot the difference between a message from your boss and an ad for something you'd never buy. So, how in the world does it do that? Well, to figure that out, we're going to build our own spam detector right here, right now. And like any good recipe, we've got to start with the basic ingredients. Okay, so here's the mission, plain and simple. We want to take a normal computer, one that knows absolutely nothing about email, and turn it into a super smart gatekeeper for our inbox. To do that, we first have to teach it what to look for. First up, we need clues. In the world of machine learning, we call these features. Think of them like little pieces of evidence. For our spam detector, a feature could be a word like free in all caps, or maybe the sender's address looks a little weird, or maybe the email is just one giant image. Each email is just a big collection of these features. All right, next ingredient, the answer key. We call this the label. It's basically the right answer for every email we have. For our project, it's super simple, right? It's just a choice between two labels, spam or not spam. That's the verdict we want our machine to eventually be able to give on its own. And finally, we have the model. You can just think of this as the brain that we're building from scratch. We're going to feed it thousands and thousands of emails, showing it all the features and the correct labels. Over time, the model starts to see the patterns. It's the engine that'll eventually look at a brand new email and predict its label. Okay, so we have our ingredients right. We've got data, which has features and labels, and we want to build a model. But how does the learning part actually happen? Well, it turns out there are three main recipes for this. First, you've got supervised learning. This is like studying for a test with flashcards. You give the machine examples where you already know the answer, and it learns to connect the dots. Then there's unsupervised learning. This is totally different. It's like being a detective. You drop the machine into a room full of data with no instructions and just say, find something interesting. It has to discover hidden patterns all on its own. And finally, there's reinforcement learning. This is basically like training a puppy. The machine, we call it an agent, learns by trial and error. It gets a treat for doing something right and, well, a penalty for doing something wrong. Eventually, it figures out the best way to win. Now, for our spam detector, this is a no-brainer, right? We have a whole bunch of emails, and we already know which ones are junk and which ones are important. We have the answer key, so we're going to use supervised learning. The machine is going to study all these labeled examples to learn the secret patterns that separate spam from the good stuff. And this brings up a really key point, the difference between learning and adaptation. You see, learning is that big, upfront process, building the whole brain from scratch. Adaptation, on the other hand, is when an already trained model just makes little tweaks over time. It's like your spam filter getting just a little bit smarter every day as new types of junk mail pop up, without needing a complete do-over. So, we did it. We've trained our model. But how do we know if it's actually any good? We can't just set it loose on our inbox and hope for the best. Nope. It's time to grade our machine to see if it passed the test. This really is the moment of truth. We need a way to measure how well it did, to see exactly where it got things right, and, more importantly, where it got things wrong. And this is its report card. It's called a confusion matrix, which sounds complicated, but it's not, I promise. It's just a simple chart that compares what the model predicted with what was actually true. So, a true positive? That's a home run. A spam email came in, and we correctly called it spam. A true negative? Another win. A good email came in, and we correctly left it alone. The other two boxes, well, that's where things get messy. And these mistakes are not created equal. A false positive is when our model takes a perfectly good email and throws it in the spam folder. That is a disaster. That could be a job offer or an important note from a loved one. On the other hand, a false negative is when a spam email slips past the filter. Yeah, it's annoying, but it's not the end of the world. So you can see, we have to avoid those false positives like the plague. This brings us to two super important ideas, precision and recall. Think of it this way. High precision means that when our model yells spam, it's almost always right. This helps us avoid those terrible false positives. High recall means our model is great at catching as much spam as possible. Now here's the catch. It's a balancing act. For our spam filter, we want really high precision. We'd rather let a couple of spam emails through than accidentally delete an important one. But imagine a model that detects cancer. In that case, you'd want the highest recall possible. You'd rather have a few false alarms than miss a single real case. It's all about tuning your model for the job. So our model gets an A+ on its test. Great precision, great recall, everything looks amazing. We're done, right? Well, not quite. There's one last, really common trap we need to avoid. And that trap is called overfitting. It's like a student who doesn't actually learn the material for a test. They just memorize the exact questions and answers from the study guide. Sure, they'll ace the practice exam, but on the real test, where the questions are a little different, they'll completely fail. An overfit model has just memorized the training data, noise and all. It hasn't learned the general rules, so it's useless on new emails it's never seen before. The opposite, underfitting, is just a model that's too simple and fails at everything. And so the real goal, the holy grail of machine learning, isn't just to do well on the test data, it's to achieve generalization. That's the ability for the model to perform well on brand new, completely unseen data out in the real world. That's what makes a model truly useful. So how do we make sure our model can generalize? We use a really clever technique called cross-validation. Instead of having just one practice exam, it's like we give our model 5 different ones. We split our data into, say, 5 sections or folds. We train the model on 4 of them and test it on the last one. Then we mix it up. We train on a different 4 sections and test on the one that was left out. We do this over and over until every single section has had a turn as the final exam. By averaging all those scores together, we get a much more reliable idea of how our model will actually perform when it's out in the wild. And that's it. From picking out features and labels, to training a model, to testing it to make sure it's ready for the real world, that's the journey of machine learning in a nutshell. We built a spam filter today, but these exact same ideas are used to recommend your next favorite movie, to help doctors diagnose diseases, even to help cars drive themselves. So, now that you know the basic recipe, what would you teach a machine to do? Thanks for joining me.